Okay, welcome to 2.6, the last section in Chapter 2, which is on one variable stats. The last lesson we talked about was 2.5, measures of central tendency. This is kind of like the opposite. Measures of central tendency is how much does the data tend to cluster around a certain value, and 2.6 is the opposite. How much does the data spread around? How much is it spread? We have different measures of doing that, just like we had different measures of central tendency, and so we'll talk about a few of them. I printed out the notes so you don't have to take them. So measures of spread are quantities that indicate how closely a set of data clusters around its central values, or how much it spreads from its central values. And the key thing is something called a deviation, which is the difference between a value and the mean. And we know how to calculate the mean. There is actually two different definitions for standard deviation. So standard deviation is a little different than a deviation. And we have something called the standard deviation for a population. We use the Greek letter mu, and we use the letter S for sample. And they actually have different formulas, right? So the formula is this. Instead of just adding up all the deviations, remember, a deviation is just a value subtract the mean, and that would be for like a population, or a deviation would equal the value minus the standard, the mean for a sample, if it was a sample, right? So this is deviation for a sample. We're using the mean of the sample. Here we're using, if it was a population, we're using the mean of a population, which is a different symbol, mu versus x bar. So a population, the standard deviation, the Greek letter sigma, is x minus mu. This is the population mean. And big N is the number in the population. How many values are in your population? X is the actual value that you're talking about. Same thing here. X is the value that you're talking about. X bar is the sample mean. Different letter. N is the number in the sample. And this minus 1, you see that there's no minus 1 here, but why is there a minus 1 here? And the reason, it's hard to explain, but it's here, when you take a sample, they will be clustered around the sample mean, not the population mean, and these two will be slightly different. It tends to overcompensate, so statistically we have a correction. We subtract 1 in the denominator, and that's to compensate for small sample sizes. If the sample size is big, if there's like 1,000 things values in your data set, then subtracting 1 is not going to make a big difference. But if you have a small sample, subtracting 1 from a small number will have an effect. So it has really no effect on a large sample size. So the formulas are a little bit different, and I'm not going to get into technicalities as why we subtract 1. We just do. All right. Variance is another term we use. That's just simply the square of the standard deviation. Again, that's the population. And if it was a sample, it would be the square of standard deviation of a sample, which is just S. We don't really use this much. People use standard deviation. People don't really use variance too much. Quartile. Quartiles divides a set of ordered data into 4 groups with equal number of values, and we have Q1, Q2, and Q3. Right. So Q2 has a special name. You guys remember what Q2 is? No?
The median?
Q2 is the median. We used that before. And there's a little bit of confusion what we actually mean by a quartile. Although a quartile is a single value, these things are single values. However, in popular culture, when people talk about quartiles, they're talking about a range. So people sometimes speak of a datum being within a quartile. What they really mean is that the data is in the quarter whose upper boundary is the quartile. So, for example, quartiles are these actual numbers. These are actual single values. But if you say something's in the third quartile, we're saying it's between Q2 and Q3. That would be the third quartile. The fourth quartile would be between Q3 and the max. That would be the fourth quartile if you're talking about a range, which a lot of times they do. But technically, that's not correct. Interquartile range is typically the third quartile minus the first quartile. Oh, it's written right there. All right. Let's flip the page and continue with some definitions. What am I trying to do here? All right. Semi-interquartile range. Semi just means half, so it's half the interquartile range. What was the interquartile range? It was just Q3 minus Q1. So the semi-interquartile range is that same number divided by 2. Just divide it in 2. In that assessment that we did, that little assignment, that correlation assignment, you did a box and whisker plot. So let's review what that is. Let's just show an example. It's a graph that summarizes a set of data by representing the first quartile, the median, and the third quartile with a box, and the lowest and highest data with the ends of lines extending from the box. So let's just do an example. Let's say we had a box, something like this. And it doesn't have to be right in the middle. You can have, let's put Q2 right there. You can put Q1 there. You can put Q3 there. So that means 50% of the data, 25% of the data is in this quartile, 25% of the data is this quartile. And what do we have at the ends of the boxes? Of the box?
Max and min?
Yeah, but it's not part of the box, it's just a straight line, right? So let's go way out here and do a max here. Let's do, again, they don't have to be the same length, right? You can put a min there. So this would be an example. And that's what you did for me on that assignment a long time ago. But more accurately is to draw something called a modified box and whisker plot, which is where you take outliers into consideration. And there's a definition for an outlier. By convention, any point that is at least 1.5 times the box length. This is the box length. This is called the interquartile range. Like Q3 minus Q1 is that length. If you're a point and you're at least 1.5 times the box length away from the box, then you're classified as an outlier, right? So just visually, I don't have values here. Would this be an outlier?
Yeah.
Yeah. So how do you know? Just by. So here's the box. What's 1.5 times the? Let's say 1.5 times the length of the box. So 50% bigger would be about that long, right? And then away from the box. So that would be anything more than about here would be considered an outlier. Does that make sense? So we'll get into more specific example later with actual numbers. So a modified one would be, let's draw the same box. And let's put this as Q3, Q2, Q1. Let's say there's no change on the min. Sorry for being a little sloppy there. And now we're going to put this maximum value is considered an outlier because it's more than 1.5 times the length of the box away from Q3. So we're going to call this an outlier, and we're not going to draw a line to the outlier. We're going to draw it to the maximum value of our data set that wasn't an outlier. So let's say that's there. So what does this point represent? This is the highest value that is not an outlier. That's what this would represent. But you don't extend the line to the outlier itself. Okay, so this is the more accurate way of doing things. And you might have outliers on the minimum side too, but I didn't do it in this example. We talked about in that correlation assignment a long time ago percentiles, right? A set of values that divides ordered data into 100 intervals. Actually, we did this in. We talked about probability distributions as well. Also, we talked about a z-score, so we should know what that is. It's just how far away are you from the mean. Basically, how many standard deviations are you away from the mean? And that's, you calculate it by the z-score of a value is the value minus the mean over the standard deviation. So we've used that before. Here's a visualization of what the interquartile range is. It's where 50% of the data lies. You got 25% here, 25% here. So it's the middle 50%. The semi-interquartile range is half that distance. Just this number divided by 2. Okay, pretty straightforward, right? Any questions with that? Yes? No? I take that as a no. Okay, let's do some examples. All right. So let's actually calculate, instead of using our calculators to calculate standard deviation, let's do it manually. To do this manually, it takes a bit of work. It's not that bad if you only have 1, 2, 3, 4, 5, 6, if you only have 6 things. But if you had 1,000 or 100 values and you want to find a standard deviation, it'd be pretty awkward, pretty difficult to do with a calculator. Wouldn't be too bad with a spreadsheet, but to do it by hand, that would take a long time. That's why calculators were invented, I guess. Okay, the following table lists the heights of the players on the senior girls volleyball team. Is this a sample? Is this a sample or a population?
A sample?
Well, I thought it was a population. How many people on the volleyball?
Right? Because it's all of the girls' volleyball team.
Yeah, I guess you have to play 6. Maybe there's some spares, but I'm going to assume that this is. I'm going to say that this equals a population. It makes a difference. If you know, actually we don't know. We're kind of assuming it's a population. Hopefully, when you have another example, it's more clear. But I'm going to assume it's a population and not a sample. All right. It makes a difference because the formula is slightly different. So we're going to assume it's a population. All right. Here are all the players. Here are all the heights. This is called, what is this called again? X minus the mean. The value minus the mean is there's a word for this.
The deviation.
Deviation. How far are you away from the mean? And this is just the deviation squared. So, and then we're going to sum them up. So, if you add all these up, just take my word for it, it's going to be 990. All right. So how do we find a deviation for Laurie? What's the first thing we have to do? Well, do we know what this is? We have to find the mean. So what is the mean? And this is a population, so it's pretty easy. How do you calculate mean again? Yeah, you add up all the values and you divide by the number and the number of values, right? So we said that this was 990 and there's 6 players, right? So the mean is 165 centimeters. All right. So the deviation for Laurie is going to be 178. Subtract the mean, which is 165, and that's going to equal 13. What's the mean? What's the deviation for Janet?
It's a negative number.
It's a negative number. You're going to have negative numbers. If you add up all the deviations, what are you going to get? what should you get?
1.
No. The mean is the average, and you can have some above the average and some below the average, right? But if you add up all the positives and negatives, you're going to get
0.
you should get 0. I mean, by definition, you will get 0. So that's why when we do standard deviation, we just can't add up all the deviations together and divide by the total number, because it's going to be 0. So we can't just simply add them. So that's why we have a more complicated formula. We have to do something by, we can't just simply add up the deviations and then divide by the number of the data set, because it's just going to equal 0. So we have to do something more complicated to get a number. That's why we use this squaring and taking the square root. Right? All right, so I'm not going to put in all these values, but this is going to equal, similarly, this is going to be 18. She's 18 above the mean. She's going to be minus 17 below the mean. She's going to be 16 above the mean. She's going to be 19 below the mean. All right. This number here is just this number squared. So the deviation squared. Right? So it's going to be 169. Negative 11 squared is negative 11 squared
121.
is 121. So the numbers are all going to be positive. When you square a negative number, they all turn into positive numbers, right? So that's one way of getting rid of, that's what we want. We want all positive numbers. So 8 minus 18 is 324. Negative 17 squared is 289. 16 squared is 256. 19 squared is 361. And if you add all these up, we're going to get 1520. All right. So first step is calculating the mean. Once you know the mean, you calculate the deviation for all the players, then calculate the square of the deviations, and then to get your final answer, the standard deviation is going to be using that formula that we did over here. Right? So it's the square root, and the square root symbol is, it's big, and encompasses the sum of all the deviations squared over n, which is the sum of all the deviations squared is just this number, over n is just 6, and that equals, anybody want to guess what the standard deviation would be? It's just a number, but it's an indication of the measure of spread. And up until now, your calculators would just give it to you, but this is how you would calculate it manually. And your answer would be 15.9. Does it have units?
No.
No. No, you're wrong. It does have units. It's the same units as the values, right? So it'd be, and it's the same units as the mean. The mean is 165 centimeters, and the measure of spread would be 15.9 centimeters. So it has the same units as the mean, or as the values that you're talking about. It also asks for the variance. What the heck is variance again? There's no symbol for variance. You can call it var if you want, or you can call it variance. There's no symbol for it. It's just, this. It's just that. It's the without the 1520. It's without the square root. It's this number squared, which is just that. 1520 divided by 6, or this number squared, and it ends up being 252.8. And it's going to be if this is a square of this, then this would also have units, but it's in units that doesn't really make much sense. So centimeter squared. Anyway, this is a minor thing. Don't worry about variance too much. This is the main value of spread that we're talking about, which is standard deviation. Variance is used less often. Lastly, determine the Z-score for Kelly and explain what it means. So what's Kelly's Z-score? Is it going to be positive or negative? She's below the mean, right? So she's going to have a negative Z-score. So what's it going to be? this. That's the formula, so it's pretty easy. So her value is 148. The mean is 165. Standard deviation is 15.9. And that's going to equal a negative number. This is negative minus 1.07. So what does that mean? What does that mean? How far away is she from the mean? She is 1.07 standard deviations below the mean. Okay. And we learned how to use z-scores earlier. Typically, I do this section before the probability section, so this year I've changed things around a little bit. Okay, can we do the backside? Is there anybody still there? I don't know if anybody's there still, but
We're still here.
all of you?
Still here, sir.
All of you?
Yeah.
Okay. All right.
Sir.
Wow, we're flying through this one because it's relatively straightforward. All right. All right. This example, I think, comes exactly out of the book, so I apologize for just using the exact example from the book, but here we go. A random survey of people at a science fiction convention asked them how many times they had seen the movie Star Wars. This book was written quite a while ago, so Star Wars, I don't know when it came out, but it's an old movie now. There's many different versions. This is talking about the original Star Wars. The raw data is shown below, and we have a lot of crazy people. How many of you have watched a movie twice, like in the theaters? Like,
Not me.
has anybody watched the same movie in the theater twice?
No.
I think I watched
Not
Titanic.
the theater, sir.
I think I watched Titanic twice in the theater. But what crazy person would watch Star Wars 30 times in the theater? Or maybe it doesn't mean theater. Maybe it means at home too. I have no idea. Okay, so if you're going to answer these questions about, determine the median, the first and third quartiles, the interquartile range, the semi-interquartile range, determine any outliers, what's the first thing you would do?
Outlier.
Yeah, but the first thing you would do
Find
is...
the mean?
Yeah, but how do you find the median and all these things? How do you do that when the data's all kind of out of order, right? Let's put it in order. We could write it here, but there's more room up here. Let's just what's the lowest number? Lowest. I see a 1.
1.
1. Let's put the 1. I'm just going to put this. I'm going to reorder it up here. So 1, and then you got a 2 there. How many 2s? You got 2 2s. 1 2 2. You got 1 2. Here's the third one. 3 3s. 3 3 3. 4. And the other 4. Yeah, 2 4s.
2 5.
2 5s. I see 1 6.
1 7.
1 7.
1 8.
1 8.
9. And then or 10, sorry.
Oh, there's 2 then. There's 2
10 30.
2 10s. Oh no, there's more than that. Then there's
16. 15.
nope. 12. I see a 12. I just did this like 10 minutes ago, so I can. 12, and then there's 15, 16, and 30. Hopefully we didn't skip anything. All right. What is the median? I think there's 20 values here. Yeah, I think there's 20 values. So what is the median? Where is it? Can somebody tell me where it is? So let's just count. Is there 20 values? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there's 20. So the median is going to be between what and what values? It's an even number, so the median is going to lie between 2 numbers if it's even. So it's going to lie between
6 and 7.
yes, no,
No?
5 and 6. It's between the 10th and the 11th, right? So if you draw a line, you're going to have 10 values below the median and 10 values above the median, and that is right here. That's right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the first half. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Second half. So this is Q2 or the median. So what is that? 5.5. Right. It's the average of between 5 and it's halfway between 5 and 6. What is Q1? Q1 is the first quartile. Remember, quartiles are individual values, but a lot of times people consider them to be a range, but mathematically it's a specific value. The first quartile is where? So it's the half of the first half. So you have 10 values. It's going to be between, it's an even number of values, so 10. It's not going to be a specific number. It's going to be between two values. It's going to be between the threes, right? 1, 2, 3, 4, 5, and then 1, 2. So it's going to, that's Q1. So the average of between 3 and 3 is 3. What's the third quartile? What's the third quartile?
So between 10 and 10.
Yeah. So between 10 and 10 is 10, right? All right. The IQR is the interquartile range. If you're doing this, put a little space here. Like we're going to do the outlier calculation here, so just don't go over here yet. So the IQR is the interquartile range, and that is just going to be what? So it's that range, right? From Q1 to Q3. And again, you're just doing the difference. You're showing me how big is the interquartile range. So it's 10 minus 3. So the interquartile range is 7. What is the semi-interquartile range? Pretty easy. Interquartile range. It's just half of that. It's just interquartile range divided by 2, which is 7 divided by 2, which is 3.5. All right. Let's see if any of these are outliers. If you were going to predict which one would be an outlier, which one would you pick? Would there be any outliers on the minimum side, on the low side? No, you wouldn't. Any outliers on the high side?
Maybe 30.
The 30, maybe the 16, maybe not. I don't know. The 30, probably the 30. But to identify something as an outlier mathematically, the convention that's been chosen is this. Let's see if there's high outliers. I'm just going to put outlier, not outliers. Okay. A high outlier is going to be, what's the definition? Where was that?
Greater than 1.5 the box length.
Well, and the box length is this, right? The IQR, right? The box length is, so away, so on the high side, we're above Q3, right? All right, so high outlier is going to be, we're starting at Q3, and it's going to be more than the third Q3 plus 1.5 times the length of the box. Oops. And the length of the box is called the IQR, interquartile range. Okay, so high outlier is going to be starting at the high end of the box, which is Q3, which is in this case what? In this case, the Q3 was 10, right? Plus 1.5, the IQR, which is the length of the box, which is 7. 10 plus 1.57, that would be that's 10 and a half. And that's going to be 20.5. So any value that's greater than 20.5 is going to be an outlier. The only one that we have greater than 20.5 is the 30. So therefore, value of 30 is an outlier on the high side. We don't expect any outliers on the low side, but let's just, if we were expecting some, what values would they have to be below? Let's just do that calculation as well. Low outlier is going to be less than a certain value. What's it going to be less than? So if you have it's going to be less than Q1, and it's going to be, again, 1.5 times the length of the box, the IQR, less than Q1. So it's going to be Q1, instead of adding, we're going to go the other direction. We're going to subtract 1.5 times the IQR. What is Q1? Q1 was 3. So this is going to be a negative number. This is, again, 3 subtract 10 and a half, which is minus 7.5. Therefore, there are no low outliers. Okay, we would have to be below minus 7.5. Everybody, you can't watch a movie less than 0 times. So, all right, prepare a modified box of the data, modified box plot. So let's just do that. You have the boxes here, so let's put 0 there, 1, 2, 3, 4, 5 there, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and that's 30. So let's make the box. You have more than enough space here. Let's do, where's the median? The median is at 5.5. So just let's draw. You can make the box as thick as you want. I'm just going to make it two boxes high. I'm going to draw it right there, between 5 and 6. 5. That's the median. This is Q2. Okay, let's draw Q1. Q1 is at 3. So let's draw 3. What about the third quartile? It's at 10. So we'll draw a line at 10. And make a box. All right, let's do the tails. The tail is the lowest number is a 1. That was a 1. So this represents the min. And we said there was an outlier. Let's put the outlier in. So that was at 30, way over here. And now we're going to extend the line. How far did we extend the line to? We're going to have a line. How far did we go?
20.5.
Why 20.5? Oh, that would be.
30.
Oh, I see. So this is the last value that you would have. No, you actually don't use that. We don't have a 20.5 in our data set. So basically what we're trying to say is the 30 is the outlier, so let's remove the outlier. Well, let's actually put it in as a dot, but let's not connect it with the line. So what's the highest one after the 30? So if you remove the 30?
16.
16. So we just go to 16 instead. So this is the highest value that is not an outlier. That's it. That's pretty straightforward, right? Okay. 2 questions and we're done. I think we're going to be pretty good. I don't know what we're doing time wise, but I have a feeling it's going to be in the 20s somewhere. 26 maybe. I'm guessing. All right. What is the data value of 8? Sorry, the data value of 8 is in which quartile? So that's quartile 1. Like these are the actual quartiles, but a lot of times people say that this range is the first quartile, that range is the second quartile, that's the third quartile, and this is the fourth quartile. So if you're using that, it would be what quartile? It would be the third quartile, right? So, sorry, in the third quartile. Why? Because it lies between Q2 and Q3. And lastly, last question is, what is the 90th percentile for this data? So let's just, somebody want to give, like, actually, let's just rewrite the numbers again from the very top. 1, 2, 2, 3, 3, 3, 4, 4, 5, 5, 6, 7, 8, 9, 10, 10, 12, 15, 16, 30. So, does anybody want to hazard a guess as to what the 90th percentile would be? Somebody just be brave. Shout out a number. What's the 90th percentile?
12 or 15?
No and no.
Yeah.
No and no.
Oh.
Both of those are wrong.
16.
And that's also wrong. Anybody else want to guess again? It's not 12. It's not 15. It's not actually any of the numbers shown, believe it or not.
Is it 18?
No, it's not 18 either.
23.
What is it?
23.
No, well, where would you get 23 from? Okay, so the 90th percentile by definition means 90% of the values are below and 10% of the values are above. So if you have 20 values, what is 10% of 20? 2 values, right? So the 90th percentile would be a line where you have 2 below, 2 above, which represents the 10%, and you would have 18 below, which would represent the 90%. So this would represent 90% of the data. This represents 20% of the data. Then we have 20 values, so 10%, sorry, 90, that should be 10. So 10% data represents 2 values, 90% of data represents 18 values. So the 90th percentile is what number? This
15.5.
15.5. The 90th percentile equals halfway between 15 and 16 equals 15.5. That is it. I'm going to stop recording. Stop. 38 minutes. How is that possible?